In this video, I will be talking about a concept I introduced in my PhD thesis called gait fragility. I came up with this concept as an alternative to what I call fall-probabilistic stability, which is, in my experience, how most people conceive of balance and gait stability. We generally think of someone or something as being stable if it is less likely to fall. Here, I will be arguing that there might be a more useful way of thinking about balance and gait than that perspective. In later videos, I will describe the gait fragility metric that I introduced in my thesis. One more thing before we get started. All of the papers and books that I mention in this video will be listed in the description below, so take a look. Okay, let's start with the question, increased stability or decreased fragility? I ask this because bipedal robot control has often consisted of designing pre-planned joint trajectories and applying control algorithms to track those trajectories with some ad hoc feedback control applied afterward. It's not clear what makes a particular gait or family of gaits stable, and it isn't necessarily understood what stable even means. There's also no accepted sense of global or universal optimality when it comes to gaits. So, is it possible that there might be a better way to think about balance than simply seeking to increase stability? Before we answer that question, let's at least try to define what people mean by stability. Fall-probabilistic stability. The most popular definitions of stability are related to a reduced risk of falling. After establishing fall avoidance as a primary gait stability objective, I have seen researchers express conclusions like the following from the paper, Bipedal Gait Recharacterization and Walking Encoding, Generalization for Stable Dynamic Walking. Quote, if a biped can track the desired walking pattern satisfactorily and the control system is stable, then walking stability is achieved automatically. Even if one accepts the conventional fall-probabilistic idea of stability, it remains difficult to accept the claim of automatically achieved walking stability from satisfactorily tracked walking patterns executed by a stable control system. Here, it is important to differentiate gait stability from control system stability, because one can easily get the two confused when considering the quote I just read. While it might be intuitive to assume that the desired pattern to be tracked will result in walking stability, a pre-planned motion sequence can easily result in unstable robot dynamics, even if tracked perfectly. In practice, gait stability is rare and fleeting. It's probably wiser to assume that a sequence is unstable until proven otherwise. One cannot prove absolute gait stability for every environment and despite any disturbance. Therefore, gait stability has a qualitative aspect for which situational context should be identified. So, a walking robot might be described as stable in specific environments or terrains, or when perturbed by certain disturbances at given points in the gait cycle. Although universal, absolute stability cannot be determined, it might be possible to compute a comparative stability metric, particularly in simulations. One can demonstrate that the application of a given gait controller results in the robot staying upright more often than when another or no gait controller at all is applied. This suggests the use of qualitative test-driven stability determinations instead of simply using quantitative stability metrics to determine robustness to disturbances. Such stability tests should include unexpected disturbances and departures from nominal terrains that are realistic. But even then, any conclusion should be a comparison of the results with what was contained, with what was obtained with other controllers, not a declaration of some sense of absolute stability or robustness. For example, in her PhD thesis, Katie Beal introduced the mean first passage time, MFPT, metric, which is analogous to the mean time to failure concept in engineering. Using the MFPT metric, it was proposed that legged locomotion researchers should seek so-called metastability, which literally means beyond stability, or stochastic stability, rather than global stability, which would be like some kind of guarantee of recovery from any possible disturbance or perturbation. Jerry Pratt and Russ Tedrake wrote a paper in which they asserted that a useful stability margin should be necessary and sufficient. By necessary, they meant that if the stability margin is outside a given range, the robot will fall. By sufficient, they meant that if the stability margin is inside a given range, the robot will not fall. They also said that two controllers should be compared based on their stability margins, that it should be possible to estimate the margin in real time for control, and that the margin should be useful in answering why the robot fell in the first place. Then they introduced the concept of capture margins, which denote maximum distances from points in a capture region to the support polygon, and suggested the use of linear inverted pendulum models to estimate those capture regions. These concepts of MFPT and capture margins, like most stability definitions and metrics, have been developed from the perspective of seeking to maximize stability. Here, stability can be defined as how likely it is that the robot can avoid falling. Gait fragility. Seeking to reasonably decrease gait instability differs from formulating the gait control problem as the minimization of fall probability in two important ways. First, reducing gait instability is not the same objective as minimizing fall probability, although they certainly correlate. For example, one could seek a less unstable gait for the purpose of achieving better energy efficiency while not considering fall risk at all. Second, when considering a reasonable decrease in gait instability, one recognizes that the acceptable level of fall risk can change, and that the extent to which one is willing to fall or to risk falling isn't constant. For example, one might be more willing to risk a fall to progress toward some goal in a certain situation. Loss aversion is the preference to minimize losses over maximizing wins, and is a prevailing attitude in human psychology, behavioral economics, and general life experience, as described in Daniel Kahneman's book, Thinking Fast and Slow. The asymmetry of loss aversion is not static, and it heavily relies upon one's reference point. A similar asymmetry exists in gait. Let's call it fall aversion. In general, we prefer avoiding falling over making progress towards some goal position. This explains the popularity of the fall-probabilistic convention of gait stability. Balance or gait stability is often described in terms of rejecting the effects of a disturbance to return to a normal state. From this perspective, the control designer seeks to mitigate disturbance effects, which are always assumed to be negative with respect to executing gait or any other controlled motion. In his book, Antifragile, Nassim Taleb showed that fragility denotes a vulnerability to and harm from anything from the following non-exhaustive list: risk, uncertainty, errors, time, disturbances, and perturbations. By this definition, robustness means that a system is impervious to the things in that list. That is, it is neither helped nor hurt by those things, while antifragility connotes that a system is improved by the things in that list. Two observations arise when considering these definitions of fragility, robustness, and antifragility. First, while most control designs seek robustness, they are in actuality fragile. Second, despite the unavoidable nature of uncertainty, model errors, disturbances, and so on, control approaches generally seek to avoid those negative things and do not consider antifragility at all. It would be a useful goal to seek to design antifragile control systems rather than robust ones. The objective would be for controllers to use perceived disturbances, uncertainties, and the like to achieve their goals instead of seeking to reject their effects and operate as if they didn't exist. Here we introduce the term gait fragility and observe that the aforementioned fragility spectrum proposed by Taleb is also exhibited in the development of human gait. The gait of the elderly is demonstrably fragile, while toddlers and healthy adults exhibit antifragile gait, in that it is improved over time by experience and with uncertainty, for example, in environment and terrain. Gait fragility is to be avoided, since it can lead to large, potentially catastrophic failures like falling from far smaller errors, disturbances, and the like, which are needed for improving antifragile gait. Earlier, we offered the objective of seeking to reasonably decrease gait instability as a potential alternative to the fall-probabilistic gait stability approach. That objective could easily produce gait fragility if the designer seeks to simply avoid uncertainty and does not design the control system to allow for adaptation upon encountering the unexpected or uncertain. Instead, if a control system decreases gait fragility The objectives of reduced gait instability and fall probability should be achieved as well. Another potential benefit to the gait fragility framework is its applicability to aperiodic gaits. Often, gait stability metrics do not account for aperiodic gait motions and are biased toward consistent periodic walking behaviors. While many, if not most, of a normal person's daily locomotion behaviors can hardly be characterized as periodic, these motions are not unstable. From the gait fragility perspective, periodicity need not be a factor in determining how fragile one's walking is. As is the case for stability, there can be no such thing as 100% or absolute antifragility. So perhaps, as is the case for entropy and thermodynamic states, every gait has some non-zero fragility by some quantitative measure. Perhaps absolute fragility does not exist at all, and fragility can only be conceptualized really in a relative sense. Relative gait fragility could be a comparison between bipeds, whether people or robots, between moments in time for the same biped, or perhaps between given instances subjected to different applied disturbances or terrain types. The gait fragility framework might potentially be more flexible and have more utility than the traditional dynamic stability and balance framework, which generally relies heavily on models which must contain inaccuracies, errors, and uncertainties. In practice, one might select gait motions that are least fragile within an acceptable range of risk that reflects appropriate fall aversion for a given scenario. For example, if one perceives a high probability of a significant increase in gait fragility, it would be prudent to perform what is generally perceived as a high-risk motion or behavior in hopes that the behavior might result in more of a decrease in fragility than a normal motion would. Or if it seems likely that a given state will not lead to a large increase in gait fragility, one might continue in a more conservative set of motions to avoid a potentially large increase in fragility. In this case, quote unquote conservative means a preference for the predetermined or default motion, while quote unquote high risk would imply a preference for a more reactive or exploratory behavior. It is useful to briefly explore how one might estimate or quantify gait fragility in practice. Losses and gains in gait fragility can be conceptualized in terms of center of mass controllability. Intuitively, a loss of center of mass controllability will result in increased fragility as well as a likelihood of falling, while a gain in center of mass controllability decreases fragility. The reader might observe in his or her own gait that a perceived risk of a loss in center of mass controllability, for example, seeing a slippery surface up ahead, results in a switch to a more conservative gait. However, as was mentioned in the previous paragraph, a rapid decrease in center of mass controllability, for example, unexpectedly stepping on a slippery surface and losing footing, often creates the expectation of a significant fragility increase and imminent fall, and a high-risk motion is executed in hopes of abruptly stopping that gain in fragility. These scenarios illustrate the effectiveness of switching between useful gaits in low fragility states while having high risk reflexive behaviors to use in high fragility states. All right, I hope you enjoyed the video. In a later video, I will talk about the gait fragility metric that I introduced in my thesis. Thanks for watching.